Okay, so we talk about balanced search tree. So, we have seen the if we have a input, if we have n element, and if we can do a random permutation before forming the tree, then after doing the random permutation, if you form the tree, then that tree will be expected to be balanced. But there is no guarantee, because that is the average case analysis, but the worst case it may be quadratic, it may not be balanced in the worst case. So, now we want a guaranteed balanced binary tree. So, that is the our this class. So, red black tree one of the example. So, we want balanced search tree, binary search tree, and this is guaranteed, no randomly build, nothing. So, we want guaranteed binary search tree, because we want the balanced tree, that is a good tree, because we can perform the query in a logarithm time if we have a balanced tree. If we can store our data in a tree which is balanced, then we can just do the query in a logarithm time, or many things we can do in a logarithm. So, there are few example of a balanced, and this is the guaranteed, this is the no randomization, this is guaranteed. Okay. So, we need guarantee, we need balanced binary search tree. So, there are some example of balanced binary search tree like AVL tree, B tree, then 2 3 4 tree, 2 3 tree, 2 3 4 tree, and say red black tree. So, these are balanced binary search tree. Okay. So, we will talk about this red black tree in more details. Okay. So, what is a red black tree? So, what is the definition? So, red black tree is a binary search tree with some properties. What are those properties? So, first of all, it is a binary search tree. So, binary search tree means we have that property. So, if you take any node in the tree x, now value of this key value of this must be all the left subtree has value less than x, all the right subtree has value greater than x. So, this is the binary search tree property. So, this is a binary search tree, that is the when that is the okay. So, now each node is colored, each node is colored, and colored by two color, colored by either red or black, red or black. So, we give the color to each node. So, and we can only use the red color or black color. So, for that, if you want to implement this, so usually for tree we have the we define the node like this, struct node. So, in data, and then we have the pointer for the left child, and maybe the right child, and maybe we need to have a pointer for the parent. Okay. So, now we have a color bit also. So, we use one bit, this is the data, we use one bit as a color, either red color or black color. Okay. So, this is if it is 1 we can use red, that is the convention we can fix by ourselves, but each node has to be colored by two color, either red or black. So, this is one property. Another property is roots are black. The root is black, and nils, leaves, the nils are basically new leaves, we will come to that what are these nils, leaves are black. Nils are basically the leaves. Leaves means may not be the not original leaves. So, we have a tree, we have the leaves. Now, we introduce some new leaves which are basically Nils to make the tree to be complete binary tree, because a node may have only one child. Okay. So, to make it complete we need to introduce these nodes Nils. Anyway, so we will come to an example. So, Nils are black, and the next property is if a node is red, then the parent has to be black. If a node is red, then the parent, then its parent must be black. So, if a node is red, if this is a red node, then the parent has to be black. The parent cannot be red. So, this is one property. So, if a node is red, then the parent has to be black. Okay. So, this is and there is another property which is very important property, which will give us the black height. So, this is the next property. So, it is telling basically, so if we take a node, so suppose this is our tree. Now, if you take a node, okay, from this node, if you just visit from this node to the leaves, if you just visit all the paths from this node to the leaves, okay, so simple path, that we are not considering the loop. Now, for each path, if we count the number of black node, so this is a path from this node to the leaf, this is another path from this node to the leaf, its leaf ancestor. So, if you just count number of black node in the path, so each path should contain same number of black node, and that number is referred as a black height of this node. Okay. So, let us write this property. All simple path from any node x to a descendant leaf have same number of black node, have the same number of black node, and that number is referred as a black height of x. So, if you take any node in the tree and if you consider a path from this node to a leaf, okay, and we count the number of black node, and then we take another path from this node to a leaf, and that same number of black node must be same. If there is 4 black node in this path, there has to be 4 black node in this path. There has to be 4 black node in the path. So, and that is why it is the unique. So, this is called black height of that node. So, this is just a number of black node from a number of black node from a path in the path from that node to its to the leaf is called black height of this node. So, if these 6 properties satisfy, then we call the tree is a red black tree, and we will see because of these properties this tree will be a balanced tree, guaranteed. There is no randomly permutation, nothing. This is guaranteed. This is guaranteed. This is if our tree is satisfying this property, then the height will be log n, that we will prove. Okay. So, let us take an example of a red black tree. Let us give an example of a red black tree. This is the definition of red black tree. These are the property our tree must satisfy, then the tree is called a red black tree. Okay. So, suppose this is our nodes, we have 7, say 3, then 18, 10, 22, 8, 11, and we have 26. Suppose this is our number is given, these are the numbers given, and this is a binary search tree. If you look at any node 10, 18. So, if you look at 18, all the subtree rooted here are less than 18, all the subtree rooted here are greater than 18. So, this is a binary search tree. Now, we want to make it a complete tree. So, we will introduce nils. Nils are basically new leaves. So, we will put nils 2, because this is having one node. So, we will introduce the nils. So, from each leaf node or from each node which is having less than, which is having one child or no child, we will put the nils, and these are our new leaves. Okay. So, this nils we introduce. Okay. So, now this is the nils, and now we need to give the color of this tree. Now, we give this root to be black, because that is one of the property, root is black. So, this is 7. So, root is black, and these nils are also black. This is one of the property we have, nils are black. Okay. Now, we need to give the color of these nodes, so that we must satisfy that 6 properties, those properties. Okay. So, which color we give to this node? So, we can give to this node black, and we can give to this node red, okay, and maybe this node red, this node red, this is black, this is also black, and this is red. This is we can try. We just suppose we assign this color. Each node, now this is a tree, binary search tree, and each node is colored. Okay, and each node is colored by red or black. Now, root is black, nils are black. So, that is one of the property. Now, if a node is red, we know parent has to be black. So, this is a red node, its parent is black. This is a red node, parent is black. This is a red node, parent is black. This is a red node, parent is black. So, that property is also satisfying. If a node is red, then the parents are black. Okay. So, now we have to see the final property, which is called black height. So, if we look at all the nodes, so if you look at this nils black height is basically 0. Now, if you look at this node, so this node, what is the black height? So, if you look at this node, so this node, if you from this node to a leaf, how many black node? Only one. This node to a leaf. So, black height of this node is basically BH, black height of this node is 1. Now, what is the black height of this node? If you take this path, so there is 1. If you take, so that black height, in the black height we must exclude the color of this X. So, let us just recall, black height is basically we take X and we consider all the nodes, black nodes in this path, okay. And if excluding the color of X, if the color of X is black, we are not counting that in the, because excluding the color of X. So, it is that has to be noted, okay. We are not counting the color of X. If the color is black, we are not adding that. So, we are excluding the color of X. Okay. So, that means black height of this is basically also 1, because it has, if you check it now, black height of this node. Now, this, consider this path from this to this, how many? 2 black node, 1, 2. Consider this path, this to this, 1, 2. Consider this path, 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 1, 2. Consider. So, from this node, if we look at all the paths, simple path from this node to the leaf, all are having same number of black node, and which is basically 2. So, the black height of this node is basically 2. Okay. And this black height of this node is now what? Now black height of this node is also, consider this path, it has 1, consider this path, this is 1, consider this is 1, because we are not counting the black of this, because that is excluded. Okay, now what is the black height of this node? So, if you take a path from this, so this is 1 2 1 2, if you take path, so from this node to this leaf, if you take the path, so we are not counting this black, so 1 2. So, just we can just check the black height of this node is basically 2. So, this is the red black tree, because it is satisfying all the properties we have listed. So, every node is colored, this is a binary search tree, every node is colored by either red or black, and if a node is, and the roots and nils are black, and if a node is red, then the parent is black, and from a given node, from a node x, if we consider the path from x to a leaf, and all the path, all such path having same number of black node, excluding the color of x, and that is called black height. So, we have that property is also satisfying. So, this is a good news, this is a red black tree. Okay. And this is balanced. What is the height of this tree? Height of this tree is 4. And how many elements are there? 1 2 3 4 5 6 7 8. Okay. So, but this is 8. We in general we have to prove that this is a balanced tree. So, this tree is balanced. Okay. But we need to prove why this is balanced, okay, for n nodes. But this is the one example of a red black tree. Now, let us prove why this tree is balanced by a theorem. So, this theorem is telling, so height of a red black tree. We will come to this example again when we will prove this theorem. Okay, so let us talk about height of a red black tree, and let us establish that this is a balanced tree. Height is log n. Height of a okay. So, this is we are proving by this theorem. So, this theorem is telling a red black tree with n nodes n keys has height h which is less than log of 2 log n plus 1. Okay. So, this is the theorem, and this is telling us height is, so this means height is order of log n. So, this is telling us balanced. So, red black tree is balanced, if we can prove this. Okay. So, how to prove this? So, to prove this we will use some intuition. Intuition is we want to remove the red nodes. Now, the question is how we can remove a red node from the tree. Okay. So, to remove the red nodes, we know if a node is red, then the parent is black. So, basically what we can do, we can merge the red node to its parent, because parent is black. So, that is the one where you can remove the red node. Okay. So, that we are going to do. So, how we can do that? So, let us just take that same example. So, to prove this, we will use that same example, and we will see how we can remove the red nodes. So, basically we merge the red node with its parent, because we know if a node is red, the parent is black. So, let us draw it this side. So, 7 3, 18, 10, 22, 8, 11, we have 26, and then we have the nils. And the nils are black, and this is red, this is black, this is also black. Okay, nils are black, and this is basically red, and these two are red. This is red, this is black, this is black. So this was our example of a red black tree. Now we want to remove the red node. So to remove, what we do? We know if a node is red, its parent is black. So we merge a red node with its parent, because we know parent is black. Okay, so if you do that, this is our original tree. If you do that, then what will be the situation? So this is red, so this we are going to merge with this. Okay, this is red, so this we are going to merge with the parent, and this too is red, so this we are going to merge with the parent. So this is the merging we are going to do. So this is this is red node, this we are going to merge with the parent. Every red node is merged with the parent. Now, so if we do that, then we will have this tree will convert into this tree. So this 7 and 18 is merged, and it has one child 3, and we have another child which is basically having 3 nodes, because this 3 node has merged. So 10, 8, 11, and we have another 22, 26. Okay, and then the nils are there. So this will having 4 nils, and this will have 3 nils, like this. Okay, so this tree will convert into this tree, and this is nothing but 2, 3, 4 tree. Why? So what is the number of leaves in this tree for each node? So number of leaves is either 2, so the number of leaves is either 2 or 3 or 4. So that's the reason it is called 2, 3, 4 tree. And this tree is balanced. This tree is very nice structure. So this tree is this tree is converted into this tree. Okay. Now we want to talk about height of this true tree. So what is the height of this tree? Suppose height of this tree is h, and height of this tree is say h prime. Okay. So suppose height of this tree is h and height of this tree is h prime. Now what we can say about relationship between h and h prime? So can you say that can you say h prime is greater than equal to h by 2? Because so we are merging the red node. So if we consider a path which is giving us the height, so if we consider a path, now when it will be equal? When there are, it is merging with half. So when there are equal number in that path, when there are equal number of red node and black node, then it will be equal. But we know if a node is red, then the parent has to be black. So if we consider any path, then the number of red node will be less than the number of black node, because that is one of the property. If a node is red, then the parent has to be black. So number of red node is less than the number of black node. So for this to be less than, we need to have red node more, which is not possible, because consider a path, if a node is red, then the parent has to be black. So in any path, the number of red node will be less than number of black node. So, that is the reason this height is the new height will be greater than h by 2, and it will be equal when the exactly same number of black and red node is there in the tree. Okay. So, this is the relationship we have. So, this is the height of this tree, this is the height of this tree. Okay. So, now what is the number of leaves over here in this tree? So, the number of leaves, so number of leaves is basically n plus 1, and this is same as here also, because we are not merging the nils, because nils are black. So, number of leaves will be same, number of leaves will be same, n plus 1. Okay. Now, this is having, each node is having either 2 child or 3 child or 4 child. Now, 2 is the minimum number of child. So, from here we can say that n plus 1 is greater than 2 to the power h prime, because if every node has 2 to the power, if every node has 2 child, then 2 to the power h prime is the minimum number of leaves it should have. So, n plus 1 must be greater than 2 to the power h prime. So, 2 to the power h or n plus 1 is less than 4 to the power h prime, but we do not need this, we will use this one. Okay. So, basically from here what we can say, h is less than 2 h prime, and which is less than equal to so 2 to the power h prime. So, that means 2 to the power, sorry, let us just, so from here 2 to the power h prime is less than equal to m plus 1. So, h prime is less than equal to log of n plus 1. So, this we are going to use here. So, h is from here what we can say, h is less than equal to 2 h prime, which is basically less than equal to 2 log of n plus 1. So, height of this tree is basically log n. So, balanced. So, balanced. So, a red black tree is balanced. So, this is guaranteed, there is no randomness, nothing. So, this is guaranteed balanced tree. So, this is a good news. So, if we can have such a tree, balanced tree, then we can perform our query search in a height time, and height is log n. So, the search or any other query can be handled in log n time. So, in the next class we will talk about the modifying operation, how we can insert. So, this is a dynamic set, how we can insert a element in a red black tree. So, modifying operation. So, that we will discuss in the next class. Thank you.